Welcome to EDU World Space.
This is chapter 21, problem number 50. We're given a semicircle of a piece of glass that has charge distributed on it. Upper side is positively charged and the lower side is negatively charged. In part A, we're asked to calculate the electric field at the center of the semicircle. So we can start with taking a length element as r d theta, for instance, and then we can calculate the differential charge on this. Since it has linear charge distribution lambda, it's going to be lambda r d theta, pardon me. And for the positive charges, as you know, the electric field at the center is going to be away, and for the negative charges, it's going to be towards the negative charge. So this portion is negatively charged and this portion is positively charged. So if we can write the differential charge element, one more thing to pay attention, it's going to make things easier for us, is the fact that when we add these two electric fields, as you can see, the horizontal portions are actually canceling each other out. So the net field is going to be down from here. We can only concern ourselves with the y component of the electric field. So the electric field, if we know the differential charge element, then dE is going to be equal to 1 over 4 pi epsilon naught, right? dq, so instead of dq, let's write lambda r d theta over r squared, assuming that this distance is r. So then if we only want to concern ourselves with the y component, the horizontal component, then we're going to take the sine of that angle, right? So this is going to be equal to dE sine theta. So let's substitute for dE. It's 1 over 4 pi epsilon naught lambda r d theta over r squared sine theta. Now also in the problem, lambda is not a uniform charge distribution. It's given to us as a function of sine theta. So also we can substitute for that 1 over 4 pi epsilon naught lambda naught sine theta r d theta over r squared, and we have one more sine theta here coming from the fact that we're dealing with the y component. So 1r is going to cancel, and we have 2 sine times sine theta, so we can write it as lambda naught sine squared theta d theta over r. Now all we need to do is then to integrate over the sine theta, the theta, right? So theta goes, as you know, as you can see here, from pi over 2 to negative pi over 2, right? Let's do it on the next page. Then EY is going to be equal to lambda naught over 4 pi epsilon naught r sine square theta, the integral d theta, right? So from negative pi over 2 to, well, from pi over 2 to negative pi over 2, so lambda naught over 4 pi epsilon naught r, these are constants. They can come out of the integral, and we're integrating our sine squared theta d theta. Now, if you want to do this, then we can look this up, right? On a math handbook, the integral of sine squared theta is going to give us theta over 2 minus sine 2 theta over 4. We're going to evaluate this again from pi over 2 to negative pi over 2. Then we're going to have lambda naught 4 pi epsilon naught r, pi over 2, right? Pi over 2 minus sine 2 times pi over 2 is pi itself over 4 minus, this time, negative pi over 2 minus sine negative pi over 4, right? So don't concern yourself with the sine pi terms. Let's put it in the bigger parenthesis here, because sine pi is 0, the sine negative pi is 0. These terms are going to actually go to 0. So all we're left with is lambda naught over 4 pi epsilon naught r. Pi over 2 is pi over 4. Pi over 4, 2 negatives make it a positive, pi over 4. So we have lambda naught over 4 pi epsilon naught r and pi over 2. Now the pi's are going to cancel out, so we have lambda naught over 2 times 4 is 8 epsilon naught r as the magnitude of the electric field. And we also know from the drawing that we have this y component is actually pointing down, which means if we want to write the E vector, the electric field vector, we have lambda naught over 8 epsilon naught r negative j hat, right? So this would be the answer to part A. Now, in part B, we are asked to determine the acceleration of an electron placed at this point. So the net force acting on this electron is going to be m times a, right? Mass times the acceleration of this electron. And that is going to be equal to the Coulomb force acting on it due to this electric field that we just calculated. So if we want to know the acceleration, we divide both sides by the mass. So the acceleration is going to be equal to QE over m. In this case, our Q is, negative E, but let's substitute for the electric field. We had just calculated it to be lambda naught over 8 epsilon naught, let me remember, epsilon naught r negative j hat, right? So we can plug everything in because lambda naught is given to us in this part of the problem as 1 microcoulomb per meter, and the radius is given to us as 1 centimeter. And we know the rest, right? We know the charge of an electron and we know the mass of an electron. Charge of an electron is negative 1.602 times 10 to the power of negative 19 coulombs divided by 9.11 times 10 to the power of negative 31 kilograms. Lambda naught is 1 times 10 to the power of negative 6 coulombs per meter, right? I did the conversion from microcoulombs to coulombs. And then in denominator, we have 8. Epsilon naught is 8.85 times 10 to the power of negative 12 coulombs squared per Newton meter square. And R is 0.01 meters, right? Still, we're in the negative j hat direction. So you can see one negative here, the other negative there, then it's going to give us something positive. It's going to give us 2.48 times 10 to the power of 17 meters per second squared, and directionally it's going to be, the acceleration must be in the positive y direction, meaning up.